Hello YouTube. Today we're going to continue looking at the philosophy of SETI. So here is the Drake equation, just to remind you, and if you've forgotten what these terms mean, you can go back to the second video to remind yourself. Now, we saw in that video that the first three terms of the equation are now fairly well understood, and the prospects for extraterrestrial life look pretty good from what we know of those first three terms. We know the basic building blocks of life are common throughout the galaxy. Even on the most conservative estimates, there are tens of millions of potentially habitable worlds in our galaxy alone. More liberal estimates put it at billions. So what we're going to do today, and in the following videos, is look at the arguments that bear on the other four factors, which of course are not nearly so well understood. Today we're going to focus on the question of the origin of life. So that's FL. That's the term FL in the Drake equation, the fraction of habitable planets on which life has developed. At this point, we simply don't know how life arose. There are a whole host of different theories for the origin of life. Some say it happened in volcanic pools, others prefer deep sea hydrothermal vents, others prefer impact craters, others suggest deep underground in subsurface rocks, etc., etc. All the theories have problems and there's no consensus. It's still a mystery. However, one key development in research on the origin of life, which is reasonably widely accepted, although it's by no means universally accepted, is the notion of an RNA world. So a major problem for theories of the origin of life is what's known as the chicken and egg problem. Nucleic acids, so DNA and RNA, carry information. They are the genetic code of the organism. Proteins function as enzymes. Enzymes accelerate chemical reactions. Now, the nucleic acids cannot replicate without the help of proteins. Yet, the nucleic acids are what encode the proteins. So we have two different types of molecules, both tightly integrated into an overall system. The nucleic acids handle the genetic information, proteins handle the metabolism, and you can't have one without the other, so it seems. It's highly improbable that this integration arose spontaneously. So, the question is, which came first? Nucleic acid or proteins? Genes or metabolism? Now, as I say, there's a general consensus that the solution to this is the RNA world. So we've long known that RNA can carry information like DNA. Many viruses have RNA genomes, but it turns out that certain RNA molecules, known as ribozymes, have complementary base pairs such that it allows them to fold into various different shapes, like proteins. And so they can function as enzymes. So the basic idea of the RNA world is that at first RNA was a replicating enzyme and it replicated itself without protein. Later it developed protein synthesis, and then of course through natural selection the proteins became increasingly efficient and they could replace the RNA enzymes. Once proteins took the role of enzymes supporting RNA replication, this then allowed DNA to replace RNA as the carrier of information. And that's understandable because DNA is more stable. So, that's obviously a very, very brief. There's a lot more to the story than that, but that's the overview. So the point is, it seems that once you have an RNA world, it's a fairly straightforward path to more complex forms of life. Once you've got the self-replicating RNA, then natural selection is going to take you to genuine life, to life as we know it, rather quickly, with near certainty. The probability of getting life from the RNA world is very, very high. Unfortunately, this doesn't help us estimate FL. The problem is that we don't know how to get to an RNA world from purely abiotic beginnings. How do you get these RNA molecules in a world without life? How do you concentrate enough RNA molecules together that they might start carrying out chemistry and metabolism and self-replication? The prebiotic synthesis of RNA is a very, very puzzling problem. So although there have been some important developments in theories of the origin of life, we're still really in the dark. I'm not going to review the scientific hypotheses in this video because that would require a whole series and it's outside of my area of knowledge. And in any case, as far as the Drake equation is concerned, the specific details aren't so important. What matters is the probability of life emerging. Now, broadly speaking, there are three views we might take about the probability of abiogenesis. The first view I'm calling inevitability. So according to inevitability, in the conditions that prevailed on the early Earth, life arose very easily. Life is a cosmic inevitability. It happens easily. It's a standard physical and chemical process. So on this view, the universe is teeming with life. Provided a planet has habitable conditions, life of some sort will almost certainly arise, and it will arise very quickly. So on this view, life is maybe analogous to something like cyclones. Whenever you have a planet with an atmosphere, you're going to get cyclones. Matter just sort of tends to organise itself in that kind of way. It just tends to organise itself so as to produce cyclones. According to inevitability, it's the same with life. Once you have the right conditions, and there's a broad class of conditions that can count as the right conditions, matter will just tend to produce life. A second view we can call common. According to common, there's some life throughout the galaxy, but the origin of life is quite difficult. It requires special conditions. It occurs often enough for many habitable planets to be inhabited. So we might say, 1 in 5 or even 1 in 100 habitable planets develop life. That would still leave us with a very large number of inhabited planets, so it's still very favourable to the Drake equation. So life isn't exactly everywhere. It's not like cyclones, but it's still common. Now, as far as SETI is concerned, there's not too much difference between this hypothesis and the inevitability hypothesis. So in this video, I'm just going to treat these as equivalent. The third view is rarity. According to rarity, the origin of life is an extremely improbable event. It's a massive stroke of luck. So the vast majority of planets remain barren. Perhaps the origin of life requires a succession of extremely improbable steps happening at just the right times in just the right combination, unlikely to have occurred anywhere else in the galaxy. So the thought is that, on rarity, the first life form arose sort of by chance, just by the very, very lucky, spontaneous arrangement of molecules that just happened by an enormous stroke of luck to be in the right place at the right time. That produced life. So this doesn't violate any physical laws, but it was almost like a miracle. A good analogy to rarity might be, take a deck of cards and shuffle it. It would of course be possible that you just happen to shuffle the cards into original deck order. That's possible. It wouldn't involve any unusual, spooky, non-physical processes. Indeed, the probability of shuffling it into original deck order is just the same as the probability of shuffling it into any other order. But what is that probability? Well, it's infinitesimally small. In fact, we can pretty much guarantee that it's never happened in all of human history. In fact, suppose that every star in the galaxy had 1 trillion planets, and each planet contained 1 trillion people, and all of these people have been shuffling a deck of cards into a new order at a rate of once per second from the beginning of the universe. The chances are, at no point will any of them have shuffled the cards back into original deck order. That's how unlikely it is. So, according to rarity, the origin of life is analogous to that. Now, rarity is rejected by almost all contemporary origin of life researchers. All of the standard theories of abiogenesis assume that life arose, from just sort of standard, normal physical and chemical processes. It wasn't a happy accident. But I think that's just a kind of pragmatic or methodological assumption, because if rarity is correct, if abiogenesis involved a bunch of highly improbable coincidences, then it's not really something we can investigate scientifically. So scientific research will just assume that there was a straightforward path to abiogenesis, and then they come up with hypotheses and have to hope that one of them is right. There's I guess a practical utility to making that assumption, but that doesn't mean that it's true. So we've got two different extremes about the origin of life. On one extreme, we have the idea that life is analogous to cyclones. It's pretty much inevitable in the right conditions. And on the other extreme, we have the idea that life is like shuffling a deck of cards into new deck order. It involves some very specific sequence of very rare, very improbable chemical reactions. And, prima facie, both of these extremes seem to be quite reasonable. At least it seems to me. I don't really have any intuition about, at least initially, I don't have any intuition about which of these might be right. So I guess let's turn to the arguments. First of all, the case for rarity. So a first argument appeals to the fact that, as far as we know, life on Earth only arose once. Spontaneous generation has long been disproven, and all life on Earth shares a common ancestor. This suggests that the emergence of life must be a very rare event. It only happened once here, it hasn't occurred again in billions of years. If life were inevitable, it should be arising frequently, it should be popping up all the time, but it doesn't. Now the problem with this argument is, well, life emerges and then it spreads. And once life has spread, all the molecules that might have been involved in a second genesis will get used for other purposes by the already living things. So even if inevitability is correct, a second emergence of life might be extremely unlikely, because the existence of life destroys the possibility of a second origin of life. So I don't think we can really conclude much from this argument. Also, it's actually worth noting that it's not actually obvious that all life on Earth does share a common ancestor. At least I don't think this has been conclusively ruled out yet. This is a pretty controversial suggestion, but see my video on the shadow biosphere. I think it's called something like, "Is there a shadow biosphere?" That there are some people who propose that there might be, or at least we haven't ruled out the possibility that there is very unusual that life that is not related to the life that we know of. That's a shadow biosphere, a biosphere that we haven't yet discovered. So that's an interesting suggestion. Okay, a second argument for rarity is the continual failure to produce life in the laboratory. You've probably heard of the Miller-Urey experiments of the 1950s, which were really striking for showing that the basic building blocks of life, the amino acids, are produced spontaneously in conditions similar to those of the early Earth when exposed to an electrical discharge that simulated lightning. Or at least the Miller-Urey experiments showed that these are produced spontaneously in conditions that were thought to be similar to the early Earth in the 1950s. However, more recently, we have different ideas about what the early Earth was like, but more recent experiments have had similar results using gases now believed to be more analogous to the early atmosphere. Anyway, the point is, when the Miller-Urey experiments were first performed, there was a lot of hope that these would be the first step towards synthetic life, but that turned out to be much harder than anticipated. Even now, more than half a century later, we're nowhere close to the synthesis of life. We're not even close to the synthesis of anything like an RNA world. Or rather, I should say, to be clear, we are actually making progress towards designing and building synthetic organisms. Craig Venter has done a lot of work on this, but obviously that's intelligent design. Experiments that involve simulating the early Earth atmosphere and then just stepping back and sort of letting that develop and seeing if life pops up, those have failed to get anywhere near life. So the thought is this suggests life is not inevitable. Life requires very special, very unusual conditions. Again, I would say this argument is inconclusive. One important point to bear in mind is that we haven't actually put that much effort into trying to create life in this way. There's just not really that much money in this kind of research. And we must also bear in mind that laboratory conditions are actually very unlike those that would have prevailed on the early Earth. And in any case, since we really have no idea on even the basic sketch of how life arose, maybe we're just trying the wrong experiments. The inevitability hypothesis doesn't entail that life arises spontaneously in just any environment with water and organic molecules. The origin of life might require quite specific conditions. It's just those conditions, although they are quite specific, will still be common enough that they obtain on almost every habitable planet. That's what the inevitabilist says. Many people tend to sort of, when they think of the origin of life, they probably think of like just some soup of organic molecules and add a bit of energy and then life emerges. And of course that's what the Miller-Urey experiments were like. You just have this soup of molecules, electrical discharge, and see what happens. But it might be a bit more specific than that. One of the more radical suggestions for the origin of life is that it occurred on the surfaces of clay minerals, which catalyzed the polymerization of RNA. Now, of course, given that this theory has been proposed, we can study it and we can run experiments using these clay minerals and we can see if abiogenesis occurs. But of course, if this theory had never been proposed, we would never have run such experiments. So similarly, there may be other possible theories that we just haven't thought of yet that would suggest experiments very different from the kinds that we're actually doing. And maybe if we did those experiments, life might pop up easily. So, the fact that we really don't have, again, we don't have even a basic idea of how life might have arisen, makes it very hard to direct experimental research. I would say that the failure to show that life arises easily in laboratory conditions doesn't really tell us anything one way or another about inevitability or rarity. Okay, one of the major objections to inevitability is that there are a wide variety of molecules that seem to be necessary for even basic life, many of which can only be synthesized and can only survive for a long time in wildly different environments that are not likely to have occurred together. Simon Conway Morris, in his book Life's Solution, chapter 4, has a really nice discussion of this point. So he says, consider the prebiotic synthesis of the nucleoside adenosine, which is a central molecule for life. Adenosine is part of adenosine triphosphate, a molecule found in all forms of life that's involved in energy transfer, and it's even more importantly, it's also a precursor to DNA and RNA. So there's no RNA world without adenosine. So adenosine is a basic, very important molecule for life. And Conway Morris tries to imagine the ideal conditions for the prebiotic production of adenosine. So he says, what would this look like? What would have to be involved in producing adenosine in a world without any life? So he says, imagine a world with a low oxygen atmosphere, and we have a large volcanic island with a series of different climatic zones. There's a rainy side, and at the summit it's cold enough and with enough snowfall that glaciers are created. There are thunderstorms that generate hydrogen cyanide that accumulates on the glacier ice. At the tip of the glaciers are partially frozen alkaline lakes. Now, one year, just for some reason, the glaciers advance and they displace the water from the alkaline lakes down to a more temperate zone of the island. Some of this ends up in an acidic hot spring, where the hydrogen cyanide and its reaction products just happen to form the molecule adenine. Very little adenine is produced, and in these conditions it won't survive long, but the water just happens to run over alkaline ground, which neutralizes the reaction. Okay, so elsewhere on the island, formaldehyde is formed, and this is swept into a series of hot pools where it's polymerized into the sugar ribose, something known as the Formose reaction. The water in these hot pools must be a neutral pH, neither acidic nor alkaline. However, the ribose will soon be destroyed in these conditions, but luckily, after just enough time for the synthesis of ribose to occur, but not too long that it's destroyed, it's carried downstream into the ice-cold water. So we've got two streams. We've got one with the adenine and one with the ribose. And the formation of adenosine requires, among other things, heat and salt. So imagine that the two streams merge and are then carried down to sea level into hot, salty pools lined with minerals. By another stroke of luck, it just happened to be a hot day, the sun evaporated the water in these pools, leaving the adenine and the ribose with the salt in the heat of the sun, finally producing adenosine. Now, of course, through all of this, there's the risk that other reaction products would interfere to prevent the production of adenosine, but we're imagining that we're lucky. So that's the story of adenosine. Anything resembling life needs much more. To get RNA, we need to produce the other nucleosides, which need to be brought together with the adenosine. These molecules will all have required their own special conditions for being produced, and they will all have risked being destroyed along the way. Then we have to hope that just by luck, the RNA molecule that's produced happens to have the property of self-replication. Obviously, the vast majority don't. So, what have we got here? It's like, there's a host of really unusual conditions that have to happen in just the right order. It's life must be very rare, surely. It requires such a specific sequence of reactions to take place in a specific order. These conditions are unlikely to have obtained, even with billions of years and billions of planets. Now, of course, we might just be on the wrong track entirely here. Maybe the emergence of life involved other types of processes that we just haven't figured out yet, types of processes that would have occurred more easily. But the defender of rarity will say, look, we can only base our estimates of the Drake equation on the information we have at hand. And given the information currently available, we really should be judging FL, the probability of abiogenesis, to be very, very low. It's a very, very long way from from basic molecules like amino acids that would have occurred on Earth and the kind of conditions that you would have on Earth, on early Earth. It's a very long way from that to anything resembling life, and it's going to require a host of very unlikely conditions. And I think that the defender of rarity could also point out, look, some phenomena do require very special conditions. Almost all the gem quality rubies in the world were created in one place near Mogok in Myanmar. About 1.7 billion years ago, near Oklo in Gabon, a natural nuclear reactor was formed when a uranium deposit became inundated with groundwater. That's the only place that this is known to have occurred. Creating gems or undergoing nuclear fission are actually very simple processes compared to life. In the context of other types of physical and chemical processes, life is very, very unusual. There really is nothing else like it. Even the simplest life forms exhibit a remarkable complexity and functional integration. So, it wouldn't be surprising if life were really very, very rare. So the defender of rarity will say. Okay, let's turn to some arguments for inevitability. First of all, some defenders of inevitability might point out that life is of course found almost everywhere on Earth. Extremophile microbes exist in all sorts of extraordinary conditions, around hydrothermal vents in temperatures exceeding 120 degrees centigrade, in acid mine drainage at lower than 0.1 pH, under extremely high pressure in rocks, hundreds of meters below the Earth. Life is everywhere. Nothing can stop it. Now, of course, this is a bad argument if it's an argument for inevitability, because life has spread to these places over millions of years of evolution. Obviously, life couldn't arise everywhere that it's currently found. The conditions required for life of some sort to survive are presumably much broader than the conditions required for it to arise in the first place. So the prevalence of life today doesn't really tell us anything about the probability of life arising. So, second, one of the most popular arguments for inevitability is what's known as the up it pops argument. The basic idea is that life arose very rapidly on Earth, so it must be probable. If life were improbable, it would have taken a very long time to arise on Earth. There would have been billions of years during which the Earth was habitable but barren. But that's not what we see. As Carl Sagan once put it very concisely, the origin of life must be a highly probable affair. As soon as conditions permit, up it pops. So what are the details here? Well, I'm taking this information from chapter 10 of Charles Cockle's book Astrobiology. So the Earth formed 4.5 billion years ago, and there's evidence that oceans formed as early as 4.4 billion years ago and would have cooled sufficiently to support life by as early as 4.3 billion years ago. So the Earth presumably was habitable at about 4.3 billion years ago. If you've got oceans, you've got the liquid water cool enough to support life on a planet like the Earth, that's habitable. And just incidentally, that terminology, GA, that means giga-annum, and it means billion years ago. So that's 4.3 billion years ago. Now, the earliest clear, undisputed evidence for life goes back about 3 billion years, and there's also fairly convincing evidence for fossils dating from about 3.5 to 3.7 billion years ago. There is other evidence which could push the origin of life back further. In fact, there's, I think, some evidence that it might be that suggests life as early as 4.1 billion years, although that's very controversial. Incidentally, one big problem when it comes to these this early life, is it can be hard to determine whether a particular structure is a fossil of a microbe or was produced by abiotic processes. There are lots of abiotic chemical reactions that can produce structures that look a lot like fossilized microbes. Similarly, many of the proposed chemical signatures of life, like things like the ratio of carbon 12 to carbon 13, there's all sorts of chemical signatures of life, but these can also be produced abiotically. So there's a lot of debate about the earliest fossils. But we can take 3.5 billion years as a reasonable estimate. Most scientists would, I think, pretty much accept that, the life about 3.5 billion years ago. So from the point of habitability 4.3 billion years ago to the evidence of the earliest life, let's say 3.5 billion years ago, I mean, what's that, about 800 million years? Of course, life must have arisen earlier than whatever was fossilized earliest. Obviously the fossil record for early Earth is extremely poor. But what we can say is, relatively soon, at least in astronomical terms, relatively soon after the Earth became habitable, life emerged. If life arises in hundreds of millions of years, if it takes less than a billion years to arise, we should expect it to be very common. At least it's going to emerge everywhere. Every habitable planet, there will be ample time on many planets for the emergence of life. So is this argument persuasive? Well, there's a major problem with this argument, pointed out by Brandon Carter. And Carter's objection appeals to a principle sometimes called the anthropic principle, although I don't really like that phrase. That phrase is used in a variety of different ways, many of which are quite controversial. Nick Bostrom has suggested that Carter is actually just appealing to a type of selection effect. So that's the terminology I will use here. So as an example of a selection effect, consider discoveries of extrasolar planets. In the early years of exoplanet discovery, all the extrasolar planets that we found were hot Jupiters. These are gas giants orbiting very close to their parent stars. Now, naively, we might look at this and assume our solar system must be extremely unusual. We've got our solar system with terrestrial planets close to the sun. We have these small rocky planets close to the sun, and we've got giant planets far away. But then every other system we've discovered has the giant planets close to the star. But that conclusion is wrong. The trouble is, it ignores the method of detection of exoplanets. The details here aren't important, but basically it turns out that large planets close to the star are by far the easiest to detect. Indeed, planets like Earth, given the methods and technology available 15 or 20 years ago, they were simply undetectable. So we've only detected hot Jupiters, not because they were the most common type of planet, but because they were the only ones we could detect. So this is a selection effect, selection bias. The sample of exoplanets that we have is biased by the instruments used to detect them. The instruments sample only a particular subset of the whole set of exoplanets. It's kind of like a sieve where only the hot Jupiters get through. Now, Carter's argument is that there may be a similar selection effect involved when we consider the origin of life on Earth. So the first point here is that every planet has a finite habitability window. This is a finite time during which life and intelligence is possible. On Earth, the habitability window is presumably about 5 billion years. Earth became habitable, as I say, around 4.3 billion years ago. Now, due to the increasing luminosity of the sun, complex life will be extinguished in about 800 million years. And all life will be extinguished in about 1 billion years. But certainly we're not going to be able to sustain intelligent life on this planet in about 800 million years. Okay, so imagine the following scenario. Assume, for the sake of argument, that the abiogenesis, the step from no life to life, is very, very difficult. It takes, on average, hundreds of billions or even trillions of years. If you have a habitable planet, it's going to take trillions of years for life to arise, on average. Now, of course, due to the finite habitability window, this is just a way of saying that on the vast majority of habitable planets, life will fail to arise. The expectation time for life to arise is much longer than the habitability window. So there will only be a few lucky planets where life just happens, just by luck, it just happens to arise much quicker than average. Now, there are other crucial steps before we get to intelligence. Once you've got life, okay, it's a long way from life to intelligence. So assume now that many of these steps are also very hard. Let's say if you have a planet harbouring life, it will take on average trillions of years for complex organisms to arise. And then from complex organisms, it takes on average trillions of years for intelligence to arise. So again, the expectation time for the other steps on the path to intelligent life is much longer than the habitability window. And like let's say other hard steps might be the evolution of photosynthesis, the emergence of eukaryotes, which are relatively large cells with nuclei. All complex multicellular organisms are composed of eukaryotic cells, so that seems to be an important step. Maybe that was very hard. Maybe the evolution of sexual reproduction, maybe that was a very hard step that was, again, important on the path to intelligence. All of those sorts of things seem to be required for intelligence. They might all be very, very hard steps. So that's what we're just assuming, like imagine that this is the case, right? So in this universe, under these assumptions, how is intelligence distributed? Well, we can say the vast majority of habitable planets never become inhabited. The vast majority of inhabited planets never develop complex life. The vast majority of planets with complex life never develop intelligence. But if you focus just on those planets with intelligence, what you will find is that intelligence will tend to have emerged very late, towards the end of the habitability window, while abiogenesis, the emergence of life, will have occurred early, towards the beginning of the habitability window. Given how hard the other steps are, if abiogenesis hadn't occurred early, then the other steps wouldn't have had time to happen. So in Carter's universe, if you are an intelligent organism, you are almost certainly going to be on a planet on which life arose very rapidly. Even though the probability of abiogenesis is very low, so the expectation time of abiogenesis is much longer than it actually took on your planet. What this means is that the fact that we are intelligent observers introduces a selection effect. Almost all intelligent observers will find themselves on planets where abiogenesis happened very early, and intelligence, as I say, will arise relatively late. And that's, of course, what we find on Earth. Life arose quickly within, I don't know, let's say 500 million years. Intelligence arose after most of the habitability window has been used up. As I say, we've got less than 1 billion years to go. I mean, if this argument isn't clear, here's an analogy which might be helpful. Suppose there's £10 million locked in a vault, and in order to access the vault, players must pick 6 combination locks just through trial and error. These players have 1 hour to pick all 6 locks. However, the locks are very, very difficult, and the average expected time for completing each lock is, let's say, between 10 to 100 hours. And the exact average expected time doesn't matter, as long as it's much longer than the actual time available. Now, what we'll find is, obviously, the vast majority of people will fail to access the 10 million. Indeed, the majority of people will fail to pick even 1 lock. But if you look at just those who are successful in getting the 10 million, almost all of those people will have done the first lock very early, within about 10 minutes. So in Carter's scenario, the first lock is analogous to the emergence of life. The final lock is analogous to intelligence, and then of course the other locks are analogous to the other hard steps on the road to intelligence. I mean, it's perhaps worth noting in support of Carter's argument that, I mean, the kind of environment required for the origin of life might tend to obtain only very early in the history of a planet. So suppose that only planets like Earth can sustain intelligent life. Well, perhaps planets like Earth tend to follow similar trajectories. For many forms of life, oxygen is toxic. Presumably it was toxic to early life. So perhaps the emergence of life requires a low oxygen environment, like the early Earth. But complex organisms and intelligence require oxygen. Anaerobic respiration simply isn't efficient enough to support complex multicellular life. The oxygen in Earth's atmosphere rose very substantially during what's known as the Great Oxygenation Event about 2.4 billion years ago, and then again it rose again about 700 million years ago. So, if this kind of picture is right, maybe what you will find is that a planet with intelligent life, abiogenesis must have occurred early. It must happen in low oxygen conditions, and then there needs to be time for oxygen to rise to support more complex life. I mean, that's just, I don't know, just a hypothesis about maybe that's the kind of trajectory that planets with intelligent life exhibit. Anyway, the point is, we have here 2 hypotheses about the origin of life. First, there's the hypothesis that the origin of life is very probable, it's almost inevitable, it occurs very easily. And then second, there's Carter's hypothesis that life is one among many hard steps on the road to intelligence. And by hard steps, I mean the expectation time for each step is much longer than the habitability window. Carter's point is the fact that life emerged rapidly just doesn't discriminate between these hypotheses. And it looks like we don't really have anything else to discriminate between these hypotheses either, right? I mean, at least prima facie, both seem to be quite plausible. How might the inevitabilist respond to Carter? Well, one way to undermine his argument is to push the time of abiogenesis further back. If we can show definitively that life arose, say, 4.2 billion years ago, well, that would only be 100 million years after the Earth became habitable. And in that case, it would be much harder to apply Carter's argument. In Carter's scenario, even on planets with intelligent observers and so an early origin of life, we wouldn't expect the origin to be too early. It would be surprising if life arose, within 50 million years. In the same way, if we're talking about think about the combination locks, if you look at the people who successfully picked a lock, still it would be very rare for somebody to pick the first lock in 10 seconds, right? So in Carter's scenario, we're looking for life to arise within, 500, 600 million years. So we might appeal to research suggesting earlier evidence for life. But as I've mentioned, that's very controversial. This response immediately suggests an alternative response, which is to push the conditions for habitability forward. Paul Davies, in his contribution to the book The Drake Equation, points out that from 4.1 to 3.8 billion years ago, the Earth underwent the late heavy bombardment, which was a period of intense cataclysmic asteroid collisions. Perhaps the planet was not habitable during this time. So maybe the Earth was habitable only about 3.8 billion years ago. Which again would mean life arose pretty quickly after it became habitable. I'm not really sure I buy Davies's argument here. The late heavy bombardment, during this time the Earth would have been inhabited by microbes. Microbes tend to be very hardy. I don't think heavy asteroid bombardment would make the planet uninhabitable for microbes unless it just obviously, if it totally vaporized the oceans, if it turned the surface molten, then they're gone. But it depends on exactly how severe the late heavy bombardment was. If it just involved things like massive tsunamis or impact winters or aerosols in the atmosphere or whatever, that wouldn't be sufficient to sterilize all microbes. Provided the oceans exist, life can survive, I think is pretty much what we would say. And furthermore, both of these responses face the problem of Mars. Mars cooled quicker than Earth, and so would have been clement for life sooner. Now, Earth and Mars are not quarantined. Through asteroid impacts, material is transferred between Earth and Mars, and we know that some microbes can in principle survive the journey. They could in principle survive the journey. If there's life on Mars, we should expect that it will soon be delivered to Earth. Soon in astronomical time. So even if life appeared rapidly on Earth once it became habitable, well, since both Earth and Mars form a slightly connected system, that doesn't block Brandon's argument. Because we actually need to start counting from the point that Mars became habitable, and that would have been earlier than on Earth. So even a very rapid emergence of life on Earth wouldn't necessarily tell us much. If rapid emergence of life on Earth doesn't discriminate between inevitability and rarity, what would? Well, we would need to examine other habitable abodes. If we found a second sample of life that originated independently, that would be very strong evidence against rarity, strong evidence against Carter's hypothesis. The discovery of life on Jupiter's moon Europa, for example, would suggest that Carter's hypothesis is wrong. But so far we're in the dark. We'll return to Carter's argument later in this series, actually, because there's another argument he's made that's sort of similar to this but draws some stronger conclusions. Anyway, one final argument against rarity. Just how rare exactly might life be? We might think that we can set a plausible lower bound. Life exists, so surely the probability of the emergence of life can't be so low that it would have been very unlikely to occur given the size of the universe. Just for example, suppose the universe contains 10 to the power of 20 planets, but then it turns out the probability of life emerging on any given planet is 1 in 10 to the power of 100. Well, that would be very surprising, given that life did in fact arise here. We would expect we would expect if the probability of the emergence of life were that low, that the universe should be completely barren. So the thought here is, even if rarity is correct, the fact that life exists sort of sets a kind of lower bound on a plausible probability of the emergence of life. Now the problem is that what rarity proposes, this idea of a sort of spontaneous assemblage of say a self-replicating RNA through just the right reactions happening at just the right time, that would be too rare. The chances against it are simply too high. It would never have happened, not even once. Manfred Eigen once calculated that for a single gene of 1,000 nucleotides, there are 10 to the power of 602 variants. The vast majority are non-functional. Only a tiny fraction could be tried out over the whole history of the universe, even assuming that habitable planets had good conditions for the synthesis of nucleotides. The probability of self-replicating RNA just happening to come into existence through the random shuffling of molecules is so low as to be absurd. And so the thought then is we can at least rule out rarity. At least we can say that matter must in some sense have some bias towards life. Matter must tend to organise itself so as to produce life. So rarity is misguided. It's not just a very unlikely fluke. Now, there are a couple of responses to this. First of all, perhaps life didn't start with RNA, but with something much simpler. Indeed, it seems like even the inevitabilist has to grant this, because it's hard to see how RNA could have arisen prebiotically through more standard processes. But then, if we're proposing a simpler system, some lifelike system before the RNA world, well, presumably chance assembly would be more plausible. More generally, I mean, it's plausible that life could have a basis other than nucleic acids and proteins. Maybe there are other types of molecules that could support life and intelligence. Any of these considered individually might be extremely unlikely to arise over the history of the universe. But it might be likely that some of the molecules from this whole set would arise. So it's kind of analogous to if you have a pack of cards, how likely is it to deal yourself a spade? Well, if you consider each individual spade, it's only 1 in 52. But since there are many spades, they're a quarter of the deck, the probability of getting a spade, an unspecified spade, is 1 in 4. Maybe it's similar with the molecules that are the basis of life. Another response to this, suggested by Christian Weidemann in his article, Is the Origin of Life a Fluke?, is that this appeal to very low probability is pretty hopeless if, as many physicists suspect, the multiverse theory is correct. This is the idea that our universe is just one among many universes. Of course, this is only speculation. There's no convincing evidence for this, but we can't rule it out. If this is true, many universes like our own might contain no life at all. Perhaps of the universes like ours, only 1 in 10 to the power of 10 contain life. The probability of life emerging might be utterly minuscule, but it's still guaranteed to occur in some places in the entire multiverse, provided the multiverse is big enough. Since we have no idea how likely the multiverse hypothesis is, we can't take the existence of life here as setting any kind of lower bound on the probability of abiogenesis. So we can't rule out the claim that maybe the first self-replicating RNA really did arise just by a complete fluke, just by, as I say, random shuffling of molecules, highly unlikely to have occurred anywhere else in the whole universe. So those were some arguments concerning the origin of life. I don't personally find any of them convincing. I still have no idea at all whether we should go for rarity or inevitability or something in between. But I hope you found that interesting. Thanks for watching.